Hello everyone, today we are going to talk about change of basis, and that's section 4.7. So before we start working with actual problems, I want to remind some important stuff about basis, right? So what is basis? Basis is a set of vectors which is spanning the whole space and linearly independent, right? Imagine that we do have a vector space V, right? And we do have some vector in it, and we also have some basis S. I'm going to write down S. It's going to consist out of vectors V1, Vn. Well, I don't know how many, but let's imagine n vectors, right? Basis. And what we can do, because basis spans a space, we can represent vector through the coordinates or as a linear combination of basis vectors, right? Linear combination is just a sum of basis vectors multiplied by some real number constants, something like this, right? And we can actually write it down like this. V in the basis S equals vector C1, C2, Cn. So basically, if you find coefficients of a linear combination in a basis representation of vector V, it's going to make mapping from vector space V, our original vector space, into Rn. And you know, Rn are n-dimensional vectors, and those vectors are looking like this: C1, C2, Cn. Sorry. So, well, we'll need to remember this. So whenever we use basis, we are transforming, or we can map all vectors from our space into Rn. And Rn is just like, n-dimensional vector space. Now, what is the problem with change of basis? Now, imagine that we do have vector space V. And in this vector space V, we have two different bases. Basis S, I'm going to call it old basis. And basis S, I'm going to call a new basis. We remember that no matter what is the basis in the space, it's going to have same amount of vectors, right? If we have n vectors here, we're going to have n vectors here. Now, imagine that we have arbitrary vector v, and we can represent it in this basis and get a set of coordinates, something like this: C1, C2, Cn, right? And also we can represent it in this basis through new basis, or like a different second basis, and we get some other set of coordinates. I'm going to label them C1 tilde, C2 tilde, and Cn tilde. Now the question is, how these two sets are going to be related? What is the relation between like one basis and another basis? If they both are working for the same space, how the coordinates are going to be related? Well, and that's actually called the problem of change of basis. So imagine that you take vector v and express it in some basis s, and you get set of coordinates. And then suddenly you need to use a different basis with different vectors. And the question is, what are going to be, how these coordinates C1, Cn are going to change if you move to a different basis? Well, guys, I'm going to consider this problem not in general, but on two-dimensional space. And we are going to see how everything works in two-dimensional space, and then maybe kind of make a generalization to n-dimensional space. So imagine that that's going to be example 1. Imagine that we have two bases. I'm going to label as old basis, and it's going to consist out of two vectors: u1 old and u2 old, two vectors. and we have new basis, and it's going to have u1 new and u2 new, and they are going to be other two basis vectors. Now imagine that, well, imagine that we have vector v expressed in old basis, and it's a c1 u1 old plus c2 u2 old. The question is going to be, I'm going to put a question mark, how v is going to look in the new basis. I shift it a little bit. So v c1 tilde u1 new plus c2 tilde u2 new. So question is, what is going to be this number and what is going to be this number if we do know this one? How we can work? Let's watch like how we are going to work. What is the general idea of how do we solve this problem? Well, what we can do, guys, we can express vector u1 old as a linear combination of these bases, new vectors. Well, because this vector u1 old belongs to vector space V, as a like any normal vector, it can be expressed through some other basis, and that's what we can do. I'm going to use letters A, u1 new, plus, let's say, B, u2 new. So just kind of, because u1 is just a vector, let's forget for a second that that's a basis vector. We can actually treat it as a normal vector and represent it as a linear combination in our basis new. Now we can do the same with my second old vector, and I'm going to use A, B, I'm going to use C and D. Just linear combination. And C and D are going to be different from A and B because U1 old and U2 old are not generally equal to each other. What then I'm going to do? Well, I'm going to plug in these expressions into my formula instead of old vectors. How it's going to help me? Well, let's look. It's going to be a little bit long, but when we do this, we are going to get the formula and then we can use the formula. We don't need to do this operation every time, like we need to change the basis. I'm going to have C1, and instead of U1 old, I'm going to write down A, U1 new, plus B, U2 new, C2, C, U1 new, plus D, U2 new. And what I'm going to do? Well, U1 new and U2 new are going to be repeated in both like components. So what I'm going to do, I'm going to combine numbers in front of the same vector. So it's going to be C1a, this one, and C2c, C2c, and multiplied by U1 new, plus now B, C1b, C1b, plus C2d, U2 new, right? And now we're going to go back a little bit. I'm going to make it smaller, and we're going to do a comparison of the coefficient in front of U1 new, and we're going to see that that's exactly the number we were searching for. And the coefficient in front of U2 new is going to be exactly the number we are searching for. So we're just going to label this one as C1 tilde and this one as C2 tilde. And these are going to be my new coordinates, right? Well, now formula looks a little bit convoluted, but not that super complicated, right? We are going to just need known coordinates C1 and C2 and these numbers A, C, B, and D. Well, guys, what I'm going to do, I'm going to rewrite this these coordinates as like components of coordinates. So I'm going to write down C1 tilde and C2 tilde. Well, as we usually write down coordinates, because they're just going to be numbers, right? And what I have, C1a plus C2c and C1, sorry, it looks like it's CB, C2. C1b plus C2d, right? I'm going to go a little bit further, and well, I see that I have C1, C1 here, and C2, C2 here. I can write it down like this. C1a, C1b plus C2a, C2b, right? And because C1 and C1 repeats here and here, I'm going to take it outside. A, B plus, I'm sorry, C2. Oh, I put instead of A, B, C, D, sorry. Did a little mistake over here and over here. Sorry, it's supposed to be C and it's supposed to be D. C and D. Wow. Now guys, what I'm going to do, I'm going to write it down as a product of matrix, which is going to look like this: A, B, C, D by a vector C1 and C2. Well, let's imagine that we do this multiplication, this matrix by vector. So my row number 1 multiplied by column number 1 is going to be AC1, C, C2. That's AC1, C, C2. And the second one, BD. Second, BC1, D, C2. BC1, D, C2. So, well, but if we skip all this and just write down the beginning of this statement and the end, we are going to get the answer to the question we posted in the beginning of this lecture. So how do we find the new coordinates if we do know old ones? So what we have here, guys, here, old coordinates, this one, new coordinates. And we see that to get new coordinates, we just need to take old coordinates and multiply by a matrix. This matrix consists out of AB and CD. What are AB? Like, it consists out of, like, if you write it down as like not sum, but kind of, maybe I should not do it. It's like this way, like two vectors. What is AB? If you go back over here in the beginning, AB are actually the coordinates of old vector in a new basis. So basically, if you write down U1 old in new is going to be AB. And I'm going to do same U2 old in new basis are going to be CD. So basically, guys, what we'll need to do, this is AB and this is CD, first column and the second column of our matrix, which we use over here. So we're going to call this a transformation matrix, and it's going to consist out of actually coordinates of old vectors in new basis. Well, it does not look very complicated. We just need to kind of remember the formula. Okay, so let's consider example. So I'm going to do like a numerical example. That's going to be example number 2. So let's consider B old basis, and it's going to consist out of two vectors, u1 old and u2 old, and these vectors are going to be next. U1 old is going to be actually 1 0, and u2 old is going to be 0 1. So my old basis is actually a standard basis. For R2, right? My new basis, B new. My W doesn't look really now like now. B new is going to consist out of U1 new, U2 new. So my new vectors are going to be U1 U is 1 2, and U2 new is going to be 1 1. Well, I am not going to check whether these two vectors are making bases, but you probably do see that they are not parallel because they are not proportional to each other, and because they're just the dimension of the space is 2, we need just two vectors to make a basis, and they're supposed to be linearly independent, which is the case with these two, right? So now we'll need to, sorry, I moved my notepad a little bit. We'll need to kind of get the old coordinates in terms of new, right? To get our matrix P. Well, let's find, so the question is going to be, what is P transformation matrix? That's going to be the question. So what we'll need to do? Well, generally speaking, we'll need to express U1 old as A U1 new plus B U2 new, right? Well, what I'm going to do, guys, I'm just going to literally solve this system. So what is my old? Old one is 1 0, right? To be A is going to be unknown. New one is 1 2 and 1 1. I think we can just solve it I don't know, by elimination or whatever. I'm going to write it down as a matrix. So I have matrix 1 2 1 1 multiplied by a known vector AB, and my right side is 1 0. I don't know, like, not necessary to solve it by specific way, but we can write down 1 1 2 1, and over here augmented matrix. Let's try to do Gaussian elimination. So I'm going to eliminate this element, right? So I'm going to have 1 1 1 here, and I'm going to multiply row number 1 by 2 and subtract 0, this 1 by 2 subtract, and this 1 by 2 subtract minus 2, right? Okay, now my next step is going to be, so that was row number 2 minus 2 row number 1, right? That's a step. This one, now I'm going to multiply row number 2 by minus 1 and get 0 1 2, right? And now I'm going to eliminate this element. So row number 1 equals row number 1 minus row number 2. I'm going to get 0 1 2, and 0 minus 1 minus 0 is 1. 1 minus 1 is 0, right? And 1 minus 2 is minus 1. Well, it looks like I solved it. So because my unknowns are AB, so my A actually going to be equal to minus 1, and my b equals to 2. That's my solution. So these are my first coordinates, which are going to make a first column of my matrix B. Now I just need to repeat this process second time, and these new vectors are going to be same. The only thing which is going to change is the right side. So I'm going to label it as 1, now it's 2. I'm going to copy the same matrix, 2, 1. My right side is going to change. Now instead of 1, 0, I'm going to have 0, 1, my second vector, right? But operations are going to be basically same, just because my operations do not depend on my right side. Okay, so I'm again going to repeat operations. So row 2 equals row 2 minus 2 row 1. I'm going to get 1, 1, 0, minus 1. Just over here, I'm going to have slightly different. Well, row 2, 2 row 1. It's going to be still 0, 1, just because row 1 has over here 0. In the next operation, row 1 equals row 1 minus row 2. Multiplication, and then like row 1 minus row 2, right? So it's a 0, 1, here minus 1, and 1, I subtract, that's a 0, and I subtract, I think it's going to be 1, right? I mean, it's minus 1 here, but if I subtract it from 0, I'm going to get 1. Well, basically that's my answer. My C equals 1, my D equals minus 1. So I got two columns, minus 1, 2, and from the second one, 1, minus 1. Well, maybe I did a mistake somewhere, but let's consider that all these answers are correct. Now I'm going to build my transformation matrix from these two columns. So that's my transformation matrix. Now, when I have transformation matrix, I can convert any vector from old basis to a new basis. Imagine that we have a vector W, and W expressed in old basis has coordinates, I don't know, 1, 5. And the question is, what is W in new basis? Oh, sorry. Well, we remember that to find W in a new basis, we are supposed to take transformation matrix and multiply it by coordinates from old. Well, the matrix is known. It's minus 1, 2, 1, minus 1, and my coordinates are 1, 5. And I'm just going to do multiplication and get my answer. So 1 by minus 1 is minus 1, 1 by 5 is plus 5, and 1 by 2 is 2, minus 5. So what I'm getting 4, and here minus 3. So these are my new coordinates. Okay. Well, since our equation for coordinates is looking this way, new coordinates equals matrix B by old coordinates. What is going to happen if I multiply this expression by inverse matrix to this one on the left? I'm going to get identity here, and I'm going to get a transformation from old basis to new, like opposite direction transformation. So it's new multiplied by inverse, and that's going to produce old. So now if you want to return back from new basis and go back to old basis, then you kind of multiply by inverse matrix to a matrix of transformation. Well, now what is going to happen in general? In general, guys, that's going to be the same transformation matrix. So if you have a basis which consists out of n vectors, not 2 vectors, so general transformation. from B old U1 UN to B new U1 tilde UN. I want to write down old and new next to each vector. I'm just going to. So what we'll need to do? We'll need to build a transformation matrix P, and it's going to consist out of out of coordinates of old basis U1 in new basis. They're going to work as columns. I'm going to separate them by commas, but when you place them in the matrix, there are no commas, right? U2 in the new base. So old in new. This is old. Old vectors and new are going to produce columns, which you are going to produce a whole matrix. Well, if you have more vectors, matrix is going to be bigger. Well, I don't know. As I'm going to label this like B old to B new. Yeah, I know in the book they mark everything with like a little bar, but I think it's a little bit confusing when we do the bar. Okay, so guys, my suggestion is to practice with this, because the idea is not very complicated. Basically, you just need to kind of have some practice, like go from one basis to another basis and apply this knowledge to, some vector. Okay, that's all about basis transformation.